Faradays and Lenz's laws D. The figure at right shows a wire that carries a time-varying current and a nearby conducting rectangular loop. So right down here at the bottom of the screen, there is our time-varying current. The dimensions of the situation are shown. Beta is a positive constant. What must be the units on beta? So we're looking at this equation here, and we want to know what the units of beta are. Current is in amps, and then we have the unit for beta, whatever that is, and then time is in seconds. So it looks to me like the unit for beta would be amps per second. And since an amp is a coulomb per second, I guess an equivalent unit, wouldn't it be coulombs per second squared? That would be okay. As time proceeds, in which direction will current flow around the loop? We can tell by the equation that the current is increasing with time, which means that the magnetic field around the wire will be increasing with time. And on this side of the wire, according to the thumbkin twist and right hand rule, where your thumb points in the direction of the current, your fingers are going to point into the page. The magnetic field on this side of the wire, I'll just draw it over here because I don't want to mess up what's in that drawing. That magnetic field is pointing into the page, and so it is increasing into the page. And Lenz's law says we don't like change, so we're going to fight that increase into the page with our thumb pointing out of the page, and that means we're going to go counterclockwise around this loop. Derive an expression for the magnitude of the EMF induced in the loop. The magnitude of the EMF, I'm going to leave the negative sign off of Faraday's law here, is going to be that. Now, generically, magnetic flux is B times A, the magnetic field multiplied by the area. But here, the magnetic field is not constant at every point. It is constant at a very thin slice, too thin for me to show. It's constant at this slice and the slice to the right and the one to the left and all the slices that make up this loop. But if that slice is a distance r away from the wire, and if it has a thickness dr, then what we need to do here is we need to instead use the calculus form of this and see what we can make of it. So let's see if we can do that. We are going to integrate r here from w up to z. R is going to go from w up to z. The magnetic field strength away from a wire is given by mu naught times the current in the wire divided by 2 pi times r. So we derived that a long time ago. And specifically here, I can be written as beta times t. So let me scratch off this I here and put beta times t. Now what's dA? dA is this little segment right in here. dA, you can see, is a little rectangle having the dimensions h and dr. This little dA portion here is going to be h dr. Now if we combine all of that, what does that give us? Let's rewrite the integral. R goes from w up to z, and we have mu naught beta t h and dr in the numerator. I'll draw the dr out to the side. Mu naught beta t, and then there's an h there. Then we have our dr, and then in the denominator we have 2 pi r. This t is a constant. So basically everything in this expression is a constant except we have dr over r to integrate then. And when you integrate dr over r, you get the log of r. The equation for the flux is going to be all of these constants, mu naught, beta, t, h, and then below that, 2 pi. And then when we integrate dr over r, we get the log of r. So if we put in those integration limits, we get that. So that's our flux right there. That's the magnetic flux that's occurring through this loop. But to find the EMF, we need to take the time derivative of that. And look at that. That's going to be pretty easy because time is just to the first power. So I think our final answer is going to be this whole same thing except without the t. U naught theta h divided by 2 pi times the log of z over w.